Okay, let's do problem 2 from last semester's exam. So we have two charges, Q1 and Q2, are fixed in space as shown. How much work must you do to move a third charge, Q3, from point A to point B? So we have these two charges which are fixed here and here, and we want to take a charge from this point and move it down here. And so this charge is 10 microcoulombs that we're going to move from here to here. So we know that the work to move a charge from one potential to the next is the charge that we're moving times the potential difference. So the potential difference between our final point from point B, starting from point A. So we have some charge Q, which is 10 microcoulombs, and we're moving it. We want to find VB minus VA, and that'll be the work that we've done. So we need to find the potential at B first, and then the potential at A. So the potential at B is the potential due to these two charges at this point. And so we saw this in the first problem on the exam also, that the potential due to a single charge is just K times the charge. Let's say this is Q, this is Q2, this is Q1. So the potential due to Q1 at this point is K Q1 over this distance. So this is 2 meters away, but KQ1 over, say, R1. And the potential due to charge 2 at this point is KQ2 over R2. And so this is the potential here due to both of those point charges. So if we add this up, we've got K Q1 is negative 2 microcoulombs, and it's 2 meters away. And Q2 is plus 2 microcoulombs, and it is 1 meter away. 2 microcoulombs, and that's 1 meter away. So this is the potential at point B. We need to do the same thing, but at point A. So the potential at A is K Q1 over the distance from here to here is 1 meter, and K Q2, and the distance from here to point A is 2 meters. So if you do these two things, you'll get, for the potential at B, 9,000 volts. You'll get negative 9,000 for this one. And so VB minus VA will be 18,000 volts. And times the charge that you're moving to find the work. So go back, you found VB minus VA was 18,000 volts. This was delta V. And so the work was the total charge that we're moving, which is Q3, so 10 microcoulombs, it's 10 to the minus 6 coulombs times 18,000, and a volt is a joule per coulomb. So joule per coulomb, coulombs will cancel. So this ends up being, let's see, that's 10 to the minus 5, 0.18 joules. And that's the final answer. Okay, so let's do part B. Human blood conducts electricity, and its electrical resistivity decreases with increasing flow rate due to an increased alignment of red blood cells. When the red blood cells are aligned, the resistivity of the blood is 0.6 ohm meters and is 0.7 ohm meters when the red blood cells are randomly oriented. So we measure the resistance of blood by filling a 1 centimeter diameter and 5 centimeter long tube, and then measuring the resistance between the ends of the tube. What resistance will you measure when the blood cells are aligned? Okay, so let's draw a picture of this. We have a tube that's 1 centimeter diameter and 5 centimeters long. And we fill this with blood. So the blood has a resistivity. We fill it with blood with the blood cells aligned. I don't know how we do that, but we do it. So the resistivity of aligned blood cells is given to us above, so as 0.6 ohm meters. So 0.6 ohm meters. And we want to find the resistance we measure between this end and this end of the tube. So the equation that we use for that is resistance is resistivity. So the resistance of this whole thing goes up with the resistivity of the material inside. It goes, let's see, goes down with cross-sectional area, and it goes up with the distance. So the length of the tube is 5 centimeters. So this is 0.6 times 0.05 meters divided by the cross-sectional area, which is pi times the radius squared. So the radius is half a centimeter, or 5 millimeters squared. So if you do this, you'll get okay, so doing this, you get 382. Oh. Okay, this is problem 2, part 3 from last semester's exam. It says at right is a resistor capacitor circuit. The circuit starts out with the switch open and both capacitors uncharged. We need to find immediately after the switch is closed, what is the current flowing out of the battery? Okay, so if it starts off uncharged, then both of these capacitors have no voltage dropped across them since there's no charge built up on the plates yet. So when we first close the circuit, we can think of these two capacitors just as wires since there's no voltage there. So all of the current flowing through the circuit can flow through this resistor, can flow through this just as a wire here, and then back to the battery. So the only resistor that it goes through is this 100 ohms. So initially the effective resistance of this circuit is just 100 ohms. And so we can use Ohm's law. V is IR, where voltage is 9 volts from the battery. The current is this initial current that we're trying to find, and the resistance is just this 100 ohms. So I is 9 volts over 100 ohms, and that's 0.09 amps. So a long time after the switch is closed, what is the charge on the 10 microfarad capacitor? So we want to find the charge here. So a long time after the switch is closed, then that means that all the capacitors are charged up, and no more current flows through these capacitors. So all of the current flows through the resistors. So the path that current's going to take after a very long time when the capacitors are charged is through this one, through this resistor, and then back. So it's going through 3 100 ohm resistors. So this whole 9 volts goes across these 3 100 ohm resistors, and since these are all equal, then we know that an equal voltage is dropped across these each of these 3 resistors. So these 9 volts there are 3 volts dropped here, 3 volts here, and then 3 volts across this one. So since this resistor has 3 volts dropped across it, that's in parallel with this capacitor, then there are 3 volts across this capacitor. So we know that charge on that capacitor is the capacitance times the voltage, and the voltage after a very long time is 3 volts. So the charge built up is 10 microfarads and 3 volts. And so we have 30 times 10 to the minus 6 coulombs. So 3 times 10 to the minus 5 coulombs. Okay. Okay, after the switch has been closed a long time, it is then opened. What is the current leaving the 10 microfarad capacitor immediately after the switch is opened? So we leave it closed for a long time, which means we still have this 3 volts across each of these resistors, and then it's open. So that means that this battery doesn't do anything anymore, and so we can have current flow from these resistors, or current flow from these capacitors through the resistors. And so what is the current leaving the 10 microfarad capacitor immediately after the switch is opened? So this capacitor will push current through this resistor and back to its other plate. So we have 3 volts, we have 3 volts initially across this resistor, and so the current that'll flow through this resistor is 3 volts through 100 ohms. 3 volts per 100 ohms is 0.03 amps. So it's 0.03 amps, leaving the 10 microfarad capacitor right after the switch is opened. Okay, so do part D. A camera flash works by using a battery to charge a 2000 microfarad capacitor and then discharging it through the flash bulb. The battery is 100 volts and the flash requires 7 joules of energy to flash properly. So to what voltage must the capacitor be charged to power the flash? So it says the flash needs 7 joules, and that's all comes from the energy stored in the capacitor. So the energy stored in the capacitor is 1/2 CV squared, and we know the capacitance, so we get that the voltage is twice 7 joules divided by the capacitance is 2000 microfarad. So 2000 times 10 to the minus 6 farad, and square root of that. If we do that, we get an answer 83.7 volts. Okay, and then if the capacitor discharges completely through the flash in 1/60th of a second, what is the time average current? Okay, so we have this voltage initially stored up on a capacitor, and then so we have some amount of charge built up on the plates of the capacitor, and we want to get rid of that charge in 1/60th of a second. So the current is the change in charge per change in time. So the change in charge is all the charge on the capacitor, which has to leave. So that is C times the voltage of the capacitor. C is the capacitance, and the time change was 1/60th of a second. So the capacitance was 2000 microfarads. The voltage it was charged to was 83.7 volts from part 1 here, and divided by 1/60th of a second. And if you solve this, you get 10 amps.